Hi, my name is Jamie, and this is my presentation for Lab 2 of Physics 2211, Motion of a Falling Object. In this presentation, I will start with a brief introduction. I'll then go into my experimental data and then the computational data. I'll then talk about the results using a graph comparing the two, and finish with a discussion answering a few questions. The purpose of this lab is to observe the motion of an object that was dropped from a specific height. In my experiment, the system is a sponge that dropped, and the surroundings are the air pushing against it and the earth pulling it downwards. These two surroundings make up the two forces acting on the system, gravity and drag. Gravity pulls the sponge down, and drag resists the movement by going upwards. These two forces don't add up to zero, which causes an acceleration on the object. This can be shown through Newton's second law, as it states that when there's a net force on an object, there's an acceleration on the object proportional to its mass. Similar to the last lab, the velocity and position update formulas will be used to calculate each respectively. For this experiment, we'll also need the formulas for gravity and drag. Gravity is found through multiplying the mass by the acceleration of gravity, 9.8 meters per second squared. Drag is directly proportional to the velocity squared by a constant of b. When the object is held as a height at rest, there's only gravity acting on it. When it's released, drag starts being applied. In the beginning, drag is less than gravity, so the object is accelerating. When the drag force is equal and opposite of gravity, net force is zero, so there is constant velocity. This velocity is known as terminal velocity. In the experiment, we made some key assumptions. The gravity force is constant and there is drag on the object, but it doesn't cancel out gravity. In the end, my data show that there is indeed drag on the object and that there are some similarities between the experimental data and the computational data. For my experiment, I dropped a sponge from a height and recorded the falling motion. I then used Tracker to obtain position versus time data. The graph for it ended up as a downward sloping parabola. This is due to the acceleration of gravity acting on the sponge. Using Tracker, I also found the initial position of the sponge and used it in my computational model. For the initial conditions of the computational model, I set mass equal to 0.017 kilograms, as that was the weight of the sponge. Initial position is negative 0.0051, and initial velocity is 0, as the object is at rest. Delta t was set to 1 over 15, as my camera recorded 15 frames a second. This part of the code is for the code with no drag, so b is set to 0 and gravity is set to 9.8. I ended my code at zero point 0.6 seconds, as that's when my tracker data stopped. The net force on the system is just gravity, which is negative mass times acceleration due to gravity. We will use the position and velocity update formulas like last lab. After the code is ran, we see a constant sloping velocity versus time graph because the net force is constant. The position graph looks very similar to the experimental one. For the code accounting for drag, the only difference is that b is no longer 0. I found the value for b through trial and error to find the final position similar to the experimental one. The F-net in this case will be gravity plus drag, which is b times velocity squared. Everything else is the same as the calculation with no drag. When we ran the code, we will see a similar position graph, but a very different velocity one. The velocity graph shows a curve in the graph that looks like it tries to flatten out. This is because the drag force is equal and opposite of gravity. The object reaches terminal velocity. I will go into details about this later. After we obtain all the data, we can plot a position versus time graph with everything. We can see that all these graphs are increasing in the negative direction. Some key differences is that the code without drag ended at a much more negative position than the other two. This is because drag, which is a force that opposes motion, is absent. The experimental data and drag code also looks like the slope is flattening out as it gets closer and closer to terminal velocity. Theoretically, the experimental and the computational model with drag should have the same graph, but it doesn't. This can be due to potential human errors, the first of which could be the object I use. The sponge was not a perfect shape and it rotated during the fall. This changed the aerodynamics and drag constant of the object. This made it so I couldn't provide a definite drag constant as shown in my graph. The code also overpredicted motion, which means that there was more drag than the code calculated. On to the discussion. The code with drag represents a potential terminal velocity the best. As explained before, terminal velocity is the velocity of an object when drag and gravity cancel each other out. As seen, the velocity flattens out here, which shows the object reaching terminal velocity. If the object was thrown downwards, it wouldn't change the terminal velocity. Getting thrown just means that it would have a faster initial velocity. Terminal velocity occurs when drag constant cancels out with gravity. Drag will slow the object down to terminal velocity, and gravity will speed it up. The terminal velocity will always be the same, though. That's it. Thank you.